Ah, ah. Okay, today I would like to go through group task 4, which was due 2 days ago. Well, in most cases, many groups did a good job, but some group, well, didn't do a good job. But I'm going to explain one way, but you don't have to do this way, but my explanation, I hope, will help you to understand better. Okay, I don't need to explain again this group task 4, but say simply we have many shafts connected together in series, and on the left-hand side and right-hand side, we have a condition, fixed condition, and at the connecting point, we apply the load. So I'm gonna explain. Okay, to solve this problem, we need to keep in mind that always three steps to follow or to consider. First one was the equilibrium equation, right? Equilibrium equation. Equilibrium equation have to be met all the time, and second, we have to have a stress-strain relations. Well, in this case, it will be a little bit different form. The stress in this case will be a torque or a force, or strain will be a deformations. Again, this force will be torque, torsions, and deformation will be angle of rotation. Now, what will be the third one to follow or make sure is that the displacement condition. Displacement conditions, right? So as you can see again, this will be a very important step in flow chart, A+1, and the top was the equilibrium, and the second procedure was a stress-strain relation, and bottom procedure was the displacement conditions. So let's consider first equilibrium equation. We have many shafts connected together. So let's say we start from the first one, okay, just starting first one, and here we consider this part as the equilibrium, or to draw the free body diagram. And we apply the torque here, is called T12. Let's say this one is the, here we have a torque T1, and here we have a torque T2. Okay, we just consider only this section. So equilibrium wise, say x directional total torque will be T2 minus T1, this is negative directions, and plus T12 is a positive direction, and this should be 0. So this is the simply step 1 equilibrium condition, and this equilibrium condition will be applied to every section, every connecting point, right? But I just wrote down here the first one. And second is a stress-strain relation, or you can say torsion rotational relations. Okay, torsion rotation. As you can see here, equilibrium applied to a torque, right? This is a torque, and here is the torque and rotation, and now displacement in this case is a rotation condition. So torque and relations and rotation, and there is a rotation condition, right? So is everything is connected together. Now, second step is the torsion rotation. In class, we learned that we have a simple phi equal TL and G or IP or GJ, right? This is the equation we have. But we have to be careful in understanding equations. See, let's say we pick one shaft, the first shaft, that is the first one, and on the right-hand side, we have a T1, and the left-hand side, of course, we have to have a T1. And here we have a angle of rotation here. We can call phi1, and here we can call phi2. So torque T1 is constant or uniform from here to at this point. That is the important point. See, this torque is within shaft, and this torque is a constant within shaft, and the angle of rotation phi is a relative rotation, say rotation of phi2 with respect to phi1. So if we write down this formula considering this, we can say phi2 minus phi1, it should be okay. There is one more step we need to do, which is that now here this is a torque, it's a force, and this is a rotation. It's much easier and convenient to express this torque as the GJL times phi. Okay, so this is a force, and this is a K stiffness and times a rotation. So I'm going to rewrite like that. You will see why I rewrite these equations. And then this one, using this symbol, we can say T1 equal, right? T1 equal, I would say, let's call just this one as a K, okay? So K, and this one is the phi2 with respect to phi1, right? So this is the one we can have. And actually, if we look at this way, left-hand side, while the same T1 will be K minus a minus phi1 plus phi2. Well, basically they are same equation. But this first equation is from right-hand side, and the bottom equation is from this torque. So torque T1, and very importantly, the angle of rotations is the all a positive in this direction. Okay, this direction and this direction. This is all a P1 and a P2. But force has to be in different direction, but the angle of rotation has to be in same directions. So these are two simple equations we obtained from this shaft. And again, seems to we do have two equations, but basically they are one equation. You will see why we need it's better to have these two equations. Okay. And importantly, we gonna rearrange this term into a matrix form. Matrix form. I'm gonna rewrite here. The first one we can say K and minus K n equal minus T1 and the second equation you can say I'm sorry, there should be a K minus K and phi1, phi2 n equal minus T1. And second equation is minus K and plus T1. Okay, so this is the one represent this shaft. So again, the stress-strain relation is usually F equal Kx for one-dimensional case. But here we have each shaft we have a 2 degrees of freedom. So this X deformation will be this 2 degrees of freedom, and forces will be a 2 degrees of freedom which act on the right hand side and left hand side. So we have a minus T1 and the other one is plus T1, and this K is a stiffness matrix. This K will be 2 by 2. Okay, please remember this equation. So here this one, okay, this one is the stress equilibrium equation applied to at these junctions, right? And this stress or torsion rotation relation is the as in here second step. Now, what is a displacement condition? Well, in this case, we don't have to consider that because at each point we just consider phi2, only one value. So when we consider others, there will be phi3 and so on. So this displacement condition at each point will be automatically met. But importantly, at the left-hand side, say starting from phi, this is, let's call phi 0, and this is a phi 1, and so on. So okay, well we call this one, sorry, we called this one is a phi1, right? And we call this one as the phi2. I need to rewrite this one. So this one is basically T1 and phi2, right? Okay. So phi1 and phi2. So displacement condition is simply phi1 equals 0, right? And phi n plus 1 equals 0. On the very right hand side, since we have a number of shaft is n, and on the right hand side we have a fixed boundary conditions. So at each point is automatically continuous, or displacement at each junction, the shaft rotating together, those conditions are automatically met. And in addition, we have to consider on the left-hand side, on the right-hand side, there's no rotation. So this is the first equilibrium equation. This is the second, a force, torsion and rotational equation. And this is the one, third step, displacement condition. Okay. Now let's extend this three apply to a next one. Okay, I'm going to just delete this. So first one, we have K, minus K, and minus K, and K. Say this one is the Phi1 and Phi2, right? And so this one will be Phi1 and Phi2, and equal minus T1 and T1. I'm sorry, T2 plus T1. Now, second one, here, as you can see that we have a T1 and T1. And second one, we had rotation Phi2 and Phi3. And here, and torsion will be T2 and T2. And in this case, we can simply use a left-hand side. This will be K minus K and minus K and K. And this will be a Phi2 and Phi3. And this will be minus T2 and plus T2. By the way, this is the shaft number 1. So I would like to call K1. And this one, this is a shaft number 2. So this will be K2. And so on. We have a repeat the equations. And another important equation we had was these equilibrium equations. T2 minus T1 plus T2. See, this one is the torque you apply. This is a given one. But T1, T2 is unknown. They are all unknown. Okay. So from here, we can say T1 minus T2 is simply T1 minus 2. See, T1 minus T2 will be T1 minus 2. And again, using this one, this equilibrium equation will apply to this T1 and this T2. And next one, there will be another one, T2 minus T3 equal T23. And of course, so on. Okay, so we like to solve all these equations, but there was a boundary condition, Phi1, Pn plus 1 equal all 0. Right? Very importantly, let's say we here, as you can see here, this one, this is the oops. This one, a Phi2, and here is the Phi2, and this is the at the same point, right? Phi2 and Phi2. Of course, they are same Phi2. They have to have a same rotation angle, but so they have to have a same Phi2, right? But here T1 and here is the T2. There's a difference. Should be a external load which we applied. Okay, that is the one very important. So let's say we combine these equations and this equation and consider this one. Let's see what we get. Okay, we combine this together. Okay, we combine those two equations and consider that one. So in this case, when we combine them, we will have a Phi1 and Phi2 and Phi3. Okay, and try to add those two equations. As you can see here, first equation will be K1 minus K2, I'm sorry, minus K1 plus first equation, okay? And there will be 0 because there is a no Phi3, right? And the second equation will be minus K1 and plus K2, I'm sorry, K1. And now this one is important because this second and these equations and that equation will be added. Okay, so here, please, if we add it, there will be K1 and there will be a K2 here. So there will be plus K2 and there will be minus K2. And then on the right-hand side, there will be a minus T1, but importantly, the second equation will be a T1 minus T2, right? Now, third equation will be this one. So minus K2 and plus K2 and 0, right? So I'm trying to have this one, okay? Okay, I will use a different color. I will use blue, these blue equations. So can see that, and Phi3, and there will be a T2, right? So here, this equation was the first equation, right? This is the first equations. And now second equation, we add here and there, this we add them. So that will be simply these equations. And the third one will be the last one, right? Will be the third equation. So what I'm trying to do is add them and express this combined equation in matrix form, which is now 3 by 3. And here, this T1 minus T2, this will become what? T1 and T2, we do not know, but what we know is the external load, which is the T12. Okay? So, and then there will be another one. You add it, you have another one. You similarly, you add 4 and 5, and you keep adding them. So this is a very typical matrix form to solve these kind of structures. I'm trying to explain this generic procedure to combine all these shafts, and you can solve them using numerical method. So just only difference, I mean, the typical behavior is that this one, okay? This is there will be some K1 and K plus is added. And very importantly, this guy is a minus and this guy is a minus. They are symmetric matrix. Symmetric matrix. So as you can imagine, if we add phi4, there will be another term plus K3, and this will be T2 minus T3, and this will be T2. Instead of this, we will be T3, and so on. Right? You can imagine how these all equations are combined then. Okay, so let's combine them. Oops. Okay. Oops. Okay, so we combine all of them. Here will be the final matrix form. K start with K1 and minus K2. I'm sorry, K1 and minus K1 and K1 plus K2. And there will be another one, a minus K2 and minus K2 and K2 plus K3 and minus K3 and minus K3 and K3 plus K4 and so on. Please pay attention that we are all zero term here. Up to the last one will be Kn, right? There will be a Kn. See, in previous term would have been Kn minus 1 plus Kn and minus Kn and minus Kn. Okay, minus Kn. And here we have a phi1 in this row, and second row we have a phi2, and so on. The last one will be so this is a phi1 and phi2. And last one will be say this one will be phi n, and this will be a phi n plus 1, right? Because we have a phi1 and phi2 and so on. At the last end, we will have a phi n plus 1, right? Starting from phi1 and phi2 and so on. And then on the right-hand side, see, we have a T1 and second term. Now we have a T12 and T3 and so on. And this last one will be a Tn. Right? So here, let's count what is known, what is unknown. See, this one is known 0 as a boundary condition on the left-hand side. See, this one is a 0, and that is a 0. And now this one is also 0. And what is the what else do we know? We know this guy. See, we know everything. What are the unknown? Well, unknowns are this one and this one. We don't know all these deformation at the junction point. This is unknown, and second unknown, and third, so on. And also this reaction force, T1 and Tn is unknown, right? So those are two unknowns. So let's count number of equation and number of unknown here. This equation, actually, the number of equations here, 1, 2, 3, and 4, 5, and here we have a n+1, right? So number of equation will be a n+1. And given these conditions, we can solve rest of unknown, number of unknowns. Unknowns are phi2 up to phi n. Okay, these are unknown, and also we don't know the T1 and Tn. Okay, let me check. Okay, so let's try to use a Excel to solve this one. Again, my point is that I mean, you don't have to solve this way, okay? But this is one very typical way of solving procedures in matrix form. This procedure is very useful. So you just you learn this procedure for your reference, okay? Now I'm gonna go open the Excel and try to solve this one. Important point here is that, say, let's consider only a matrix, because this is a 0, this is a 0, which are already known. So we don't have to solve the first equation and last equation. We only pay attention to this one. Okay, we pay only attention to this equation. So here I will call this first matrix, and then there is a consistency and I will that one and that and that, and this will be easily extended. So let's just consider this. We have a four shaft, 1, 2, 3, 4 shaft. Okay, so this will be we have a 4 shaft. See, each one we have a K1. So let's say we have a K, I will call K matrix, okay? K, I will call K shaft. Okay, so this will be K shaft 1, K shaft 2, and so on. And I will just select this much as the equations, create, and here. So here, as you can see here, shaft K shaft 1, where K shaft 1 can be easily calculated from Gj divided by L. But here, that I'm not going to pay attention. I'm going to just use equal. So, for example, let's just use this one is 1, 2, and some different number. Well, okay, let's have all same number. And here, equal index K shaft, comma 1. So this one will be to refer to this one, and this one will be minus index K shaft, comma 1. And this one will be simply same as this one. Oops, this one. Oh, sorry. There is some. It's a 1. So as you can see, we are entering this term. Okay. So plus a 2, and this one will be a 2, and then we simply copy, okay, copy and paste, and see this one now will be 2 and 3. Well, so this one now minus K3, right? Minus K3. So this one will be minus K3. And this one will be asymmetric. So we keep doing that. We can just copy and paste and so on. For that purpose, what we can do is that this is a 2, and this is a 2, 3, and this is a 3. I mean, same as that one, right? Okay, I will just copy these terms and change. This one will be 3 and 4. And this one, we just copy. And this one, we just copy and copy. And this one, copy. And this copy. And this copy. We let's correct the equations. This one is a 3, 4. And this one should be 4. And this one should be 4, 5. Very consistent, right? That's the one of the point. And this will be 5. And this one will be a 4, 5. And this will be 5 and 6. So 4, 5, and this one is a 3, 4. This is a 2, 3, and this is a 1, 2. Of course, others are all 0. Okay, this one I forgot to say here. Because we don't consider these terms, there will be a 0. So last column, we don't need to consider that. Only this part, right? Only that part. Only this one, and this, and that. Let's rearrange this. This is a K shaft, and here we can have a forces. Okay, this will be a force. I will call this one as, oops. This one as I will call torque. And this one I can this. Now the displacement, or rotation. This is the rotation. This will be a rotations. And let's say we apply torque all 1 at the junctions, and this rotation we can easily calculate by invert this matrix. So let's call this one as the K matrix. See, this is a K matrix. I will write this one here. K matrix and rotation and torque. And so here, we simply can say matrix inverse M mult and M inverse K matrix and K inverse comma torque. Okay, so that is the rotations. Okay, that is a rotations. Okay, let me double check. Okay, let me double check. The problem I'm trying to solve was the we have a 1, 2, 3, 4. So 1, 2, 3, 4. Okay, so we had 1, okay, 1 and 2 and 3 and 4. Let me see, something is not, okay, I need some time to, okay. Okay, I'm gonna clarify the case we try to solve, okay? And this one was the K matrix, and there will be a rotations, and there will be torque we applied at each junctions. Since this P1 on the left-hand side, this one, this P1, okay, this left-hand side, these are given as the given equal 0. So this will be this one. And the last one is also a given, which is the last one here. So basically we consider 1, 2, 3, 4, 5, 6, and unknowns are P2, 3, 4, 5, 6. So basically this is the 5 unknown. So this one actually P2 and P3 and 4 and 5 and 6. Now the torque we apply is here. Okay, here we apply torque 1, 2. See here, torque 1, 2, and torque 1, 2, 3, and so on up to here. So this is the case. So this is the case for 6 shaft. And rotations, it will be 2.5 and 4, 4.5, and K and 2.5 and things. And of course, to calculate this K shaft, to be just consistent, and you can say G and J and length, right? So I will call G shear. Only one character is not recommended. J is the inertia. So let's give a name here. And then, well, double check, this is a name. And K stiffness is simply what? Simply G shear times and J inertia divided by length. So if you give any numbers, you can see that each K stiffness will be automatically calculated. Oops. And this one is simply copy and paste. Okay, so as you can see here, this one will be sharped. This is a sharped number, and this will be a sharped number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or whatever number. You can easily extend it. And here we consider sharped number 6, up to 6 here. Okay, this is the one we used. And make sure each one, each stiffness, as you can see here, we sharped 1 plus 2 and 2 and so on, 2, 3, minus 3, and 3, 4, minus 4, and 4, 5, and minus 5. Okay, this is very typical structural problems, and torque you apply at each junctions. Okay, if we consider more than 6, well, you can extend it. Okay, you can extend it, this stiffness, and you can make a little adjustment. You can easily cover as many shafts as you like. Of course, you can program this simple one. Actually, this generalize of this procedure is called computer-aided engineering. Is a basis for energy method, basis for all the programming, structural analysis, and this is a very similar to a finite element method. Okay, so I intentionally explain this way. I mean, you don't have to solve this way, but I intentionally explain this way to help you to understand or extend the concept of these numerical solutions. If needed, we can continue to further, but this one I will save and then upload. Okay. Today I'm gonna stop the class here, and we will and for the midterm there will be I will say that I want to say that there will be a problem which could be very similar to this problem. Okay, please exercise more and practice more and study more about these kind of connections and how to solve it. Okay, today this will end of today's class. Okay, thank you.